All right, today we're going to go ahead and introduce the concept of pH. So pH comes from puissance de hydrogène, which loosely translates to power of hydrogen. So instead of writing hydronium or hydroxide concentrations in terms of molarity, what has been adapted is a pH scale. And this scale, I'm sure that you've used in biology. We always said it ranged from values from 1 to 14. We're going to expand on that a little bit, but what we want to do is we want to come up with a qualitative definition so you can see how pH is actually calculated. So pH is equal to the negative log of H3O plus, or sometimes you'll see it written as negative log of H plus, because recall that hydronium and H plus we'll use interchangeably. So if you're ever given a pH and you are asked to solve for the hydronium concentration, you will want to go through and use some of your algebra skills. And so to cancel out, because this is a log base 10, we'll go 10 to the negative pH is equal to the concentration of H3O plus. So this will be useful as we go between concentration and pH and from pH back to concentration. So let's go ahead and try finding the pH of a few solutions. So in this case, I'm just going to give you the H3O plus concentration. We'll go through some more examples as we go. But here's three examples. So we have the concentration of H3O plus is equal to 10 to the negative second molar. So since we know that pH is equal to the negative log of H3O plus, we can just plug right in. So pH for the first one would be equal to the negative log of 10 to the negative second molar. Whenever you plug this in your calculator, you will get the pH of 2, which we know that a pH less than 7 indicates that the solution is in fact acidic. Please note that whenever you're plugging this in your calculator, you have to make sure that you have this negative sign before the log, and also don't forget if you have a negative sign in your exponent there. So on our next example, we'll see that pH, again, is equal to negative log of H3O plus concentration. So here, the concentration is 10 to the negative 12th molar. And so this equals 12. And we know that pHs that are greater than 7 are considered to be basic. So what we'll see is as the concentration of H3O plus is decreasing, our pH is increasing. And then finally, for this last example, we have pH is equal to the negative log of our concentration, which is 10 to the negative 7th molar, and this equals 7. So this would mean that our solution is in fact neutral. So we'll see the pH scale a lot, but now that we're in a different class, we're going to introduce this concept of pOH. So what we want to do is we want to think about where we started with pH. So recall that pH is equal to the negative log of H3O plus. So now we're going to go through and try to compare this to the hydroxide concentration instead of the hydronium concentration. So pOH is going to be equal to the negative log of the concentration of OH minus. And throughout the rest of this unit, what I would kind of recommend you do is anytime you see a lowercase p followed by something else, the lowercase p means adds negative log in front of it. So if we're looking for pOH, it's the negative log of the OH minus concentration, which means that OH minus concentration would be equal to 10 to the negative pOH. So is there a relationship between pH and pOH? Yes, there is, and we've actually already seen this in a different form looking at kW. So again, we're going to assume that the temperature is equal to 298. So we know that kW is equal to 1 times 10 to the negative 14th. And then that expression is the H3O plus, so the hydronium concentration, times the hydroxide concentration. And so what we can do is we can go ahead and use our law of logarithms. So if we know that the log of A times B is equal to log A plus log B, we can go ahead and take the negative log of this entire expression right here. So if we take the negative log of 1 times 10 to the negative 14th, we get 14 is equal to negative log of H3O plus the negative log of OH minus. And what we know is that this right here, negative log of H3O plus, is equal to pH. And this right here, negative log of OH minus, is equal to POH. So this expression, pH plus POH, is equal to 14. So this is a really useful relationship as we are trying to compare pH and POH, and then looking at the hydronium and the hydroxide concentrations. So as we go on, here's a fairly common graphic of what you'll see of common pHs of different household items that you'd see. But you can see that anything above 7 is considered to be basic. Anything with a pH below 7 is considered to be acidic. And anything right here in this range of 7 is neutral. So we will tend to focus on these calculations, and I'll also show you later on another way that we use indicators to determine whether something is acidic or basic. But let's go ahead and end this lecture by actually calculating the pH from a concentration, and then we will try to go through and determine whether the solution is acidic, basic, or neutral. So I'm actually giving you the exact same problem that we used on a previous lecture exploring KW, where we compared the concentration of H3O plus versus OH minus. So here I'm going to use pH, and we're going to determine whether it is acidic or basic. So again, by now we know that pH is equal to the negative log of H3O plus. In these problems so far, it's been nice because I've just been telling you explicitly what the H3O plus concentration is. So we can just plug in. So we have the negative log of 2.5 times 10 to the negative third molar. And when we plug that in, the pH is equal to 2.6. Okay, since our pH is less than 7, this means our solution is acidic. So for most people, I would say that using pH tends to be a little more intuitive. Instead of using KW, you'll arrive at the exact same answer regardless whether you use pH or KW. But a lot of people prefer to use pH. So that concludes this lecture. Our next one, we'll go ahead and start to look at some specific examples of pH.